future graduate student, Pierre Goussard, and he, for some while, he disappeared in Africa, and so for this reason I dropped this subject. And well, that's also fascinated me always, the general relativity, which is kind of far away from mainstream of many. Well, there are people who doing general relativity, and there are other people, and then do not communicate. So I like very much to break this tradition. And my aim is twofold. Actually, I try to I will try to do the one. I'll share the screen. There are two questions. First question is so the maybe main one is just what is the question of symmetry, symmetry of general relativity. And I'll explain a little bit relativity. And what's the problem with that is the following. So, well, for example, if we speak about four-dimensional, I'll deal with general relativity in any dimension. But in four-dimensional, for example, the symmetry group, natural symmetry group of Einstein action, this is just, well, it's topological theory, so the group is the diffeomorphism group of D4, of R4. But on the other hand, the phase space of the theory, well, it's not literally the case, but phase space of general relativity. This is the space of, well, cotangent bundle to the space of metric on R3, because, well, phase space is always related to the time slice. So it's R3. And the question is how the group, which actually diffeomorphism in R4, acts of something related to three-dimensional space. And my answer that is we are dealing actually with groupoid and not the group. And what I'll try to convince you that and it seems to me that the group, it's, well, this is some groupoid which is the groupoid of the world, because, well, general relativity is this theory. Well, the first.
Sorry, Volodya, I have a naive question. But how is it if we look just at the gauge theory? There, you would also think that this is a gauge group of the space-time, but then when you go to the phase space, you have to restrict it to the time slice. So how is it different from what's going on?
Well, different. For example, well, one of the main difference perhaps, because the gauge group, for example, if you have gauge group of R4, you have a map from R4 gauge group of R4 to gauge group of R3, because you just can restrict the a function with value in the gauge in R4 to R3. But if you have a diffeomorphism, you have R4 and you have R3 in it, and you can restrict to this slice. However, if you have a diffeomorphism, then the diffeomorphism moves this slice somehow, and you cannot restrict a diffeomorphism to a slice. It's something which is not doesn't form a group.
Okay, thank you.
And that's the main. Well, the diffeomorphism of R4 is a subquotient actually of diffeomorphism of R3 is the subquotient of diffeomorphism of R4 and not a quotient. And that's the main problem.
Is it a kind of action groupoid on the space of slices?
Right, the space of slices plus the space of solutions of Einstein equation. So this is I'll give a definition in a short while.
There should be some constraints perhaps when you just write in this Hamiltonian description of general relativity.
Of course, it's just a standard. Yes, of course, there are some restrictions. So you have actually some subspace in the space where
Yeah.
kind of Gauss-Kadatze equations. Which,
Okay. Yeah.
and it's also related to the action of to the question of moment math. So some well, you can use it using the moment math. You can introduce this constraint. And the second, actually, which were our starting point, that one of the main difficulties in dealing with general relativity, that it's just a huge theory. So it means that very heavy formula. So my aim will be to simplify formulas. Formula of general relativity, and so, for example, I follow my my advisor Vladimir Arnold, who hated indices. So I'll try to write it really general relativity without any indices. And this part I've presented in another Poisson conference in Timisoara some years ago, and so well, but I do not suppose that somebody remembers what I was speaking there. So this is actually the same subject. So first of all, I'll reformulate my my theory in some different way, and then I'll try to well speak. Actually, this question is most interesting for me, but here I am going to teach a lot, to cheat a lot as 1st of April, and here is well cheating will be unintentional. So the first idea that usual approach on general relativity, so the main field is a metric. So we will, instead of that, some preliminary definitions. So first I start with, well, first of all, I'm dealing the general relativity. N is the dimension of the manifold. Which I'll denote by M, which is on which we are studying metrics. So let's introduce the E is an E round, is a Euclidean pseudo Euclidean vector space. So space provided with a non-degenerate matrix, scalar products, and let the objects which I'll do the following. So omega pq will be the forms of M will be Q forms on M with value in the Clifford algebra of E. So a little recall what is the Clifford algebra. So Clifford P, sorry. So Clifford algebra of P is an algebra just generated by the element V belonging to E with the relations that V1, V2 plus V2, V1 equals to the scalar product of V1, V2. And I'll very much will use the fact that Clifford algebra of E is actually isomorphic to the exterior algebra of E. So this is this isomorphism is not in, of course, it's not an isomorphism as algebras, but this is not isomorphism as a modulus of over lambda. So there is an action of well, lambda of E acts on Clifford algebra of E to.
So you kind of use a fixed quantization, so like while quantization or something.
Yeah, like while quantization. But this is a contrary to Weil group. This is really canonical isomorphism.
Well, Weil is canonical in a certain sense as well.
In a certain sense, also canonical.
Yes. So it's not filtration. P is gradient in this case, right? So anticipate what you're going to say.
Yeah, I'm saying that Clifford will be grading, and so for this reason, I just use it. By definition, Clifford of there is this map which is maybe I should say that is defined by V tensor A goes to VA plus minus 1 to the degree of AV, and this is one can verify that it's really an action of lambda on Clifford, and this is a Clifford product on the right. So you can, as a module, this is
so P's degree. So it's so you treat it as a Z-graded vector space rather than
it's Z-graded vector space rather than Z2 graded.
Because it's filtered algebra. It's not graded algebra. It's filtered algebra.
Yeah, but I claim, of course, as an algebra is filtered, but as a module over lambda is graded.
Yeah. Yes. Sure. Yeah. Thank you.
This is just so there is some way to grade it, but of course, this grading is not incompatible with product. So there is such an isomorphism which I will use very much. And also I will use another object on this, which is called supertrace. So supertrace is a map from Clifford algebra of E to complex numbers, which is with the property that the supertrace of AB is minus 1 to the power degree of A, degree of B, supertrace of B. And this is actually the supertrace of Clifford N is non-zero, and Clifford supertrace of all other supertraces is 0. It just takes the highest component. There are plenty of definitions of this map.
So like Berezin integral. So
it's like Berezin integral. It's like Berezin integral in terms of if you consider just as the odd space that is Berezin. I don't think.
It's like a symbol map, and you integrate the symbol.
Yeah. Right. Exactly. Or you can say that you can take spinor representations of it. You have two spinor representations, and you take difference of traces in two spinor representations.
Yes.
It's another way to view the same thing. So this is a Clifford P is 0. It's 0 C. P is different than that. So it's just singles out the highest component. This is just an object which I'm going to discuss, and then instead of metric, I'll use what is called Palatini formalism for general relativity. And instead of metric, I'll introduce the element which is theta, which is Hilbert. It's the name for that. And this is theta is just an element. It's one form with values in it's just the Clifford algebra. So it's of course the same thing as omega 1 with values in my space E. And I require that another requirement that theta will be non-degenerate. As a map from the tangent bundle to M to E at any point. So it's if you have an element of the space, you can automatically get a map from tangent bundle to this Euclidean space. But since the dimensions are the same, you can require that this map be in isomorphism. And since this space has a metric, so you automatically get from from theta, you can reconstruct the metric on E. And very simple observation, theta prime induces the same metric. On M as theta if theta prime is just conjugate G if is equal to perhaps I should say okay, I'll write I'll say the d theta G minus 1 theta G, where G is an element of just the functions omega 0 on M with values in orthogonal group O of E. So, well, I write in this way the action of the orthogonal group on Euclidean space. So you have omega 0. So it's a function, you just conjugate.
Sorry, does it mean that you embed O of E into Cliff?
Yeah, well, yeah, of course. It's just maybe it's better to say that yeah, I O of E is a subgroup of Cliff.
Or better say, isn't it true? Like some kind of pin is a subgroup of Cliff, and for conjugation it probably doesn't matter, or what?
Yeah, pin. Well, pin is well, I consider spin is a just connected component of pin. So this is just I require the O. And not. Yeah. Well, for conjugation, it doesn't matter, of course. So if you consider this is an element of the Clifford, it's a functional value of Clifford algebra, it would be just conjugation. Because the action of that is by conjugation.
There's a question in the chat, which I also have. What was the E in this context? Is it anything still, or?
Sorry, E is a just fixed once forever Euclidean vector space
of the same dimension as M.
Of the same dimension as M, exactly.
Okay.
Exactly.
So you define metric on M by requiring that your Hilbert is orthonormal frame.
Yeah, right. It's just the same thing. Yeah, and of course, if you change orthonormal frame by the orthogonal transformation, it defines the same metric.
So Hilbert is the same as frame or repair mobile. So.
Yes, yeah, it's repair mobile. Frame. Well, what else is? Yeah, maybe some other terms also. Yeah, there's plenty of.
So in physics, it's Hilbert. So, but in your case, it's Hilbert.
Hilbert because I didn't fix
it's
the
many.
dimension.
Yeah.
Yeah, many. Well, it could be. It could. Well, I was so far I did not. Well, the dimension 4 is kind of distinguished, but so far it's not. So this is my Hilbert or repair mobile, and then I want to say the following: that we using this object, I can identify locally. Well, also so far everything is local, so M has no topology. Everything is local, and so I can identify the tangent bundle with the trivial bundle. So theta gives you this map is also can be seen as identification of trivial bundle with tangent bundle, and therefore, if you have a connection in tangent bundle, then you get a connection in trivial bundle and vice versa. So a connection in a trivial bundle the trivial bundle M times E orthogonal, well, is given by preserving metric can be given by connection form. Well, usually it's well, a form with value in the algebra of orthogonal group, but well, there is a simple observation in bracket that orthogonal group is isomorphic to lambda 2 of E, orthogonal Lie algebra. Lie algebra of N is isomorphic to the well, to this, or which is the same thing as the Clifford 2 of E. And I would denote that the connection form is a form with value in Lie algebra, but using this isomorphism, we can identify that connection form will be omega in omega 2, 1 of M. So therefore, it's an well, once again, I repeat that it's a omega 1 form on M with value in the Clifford algebra 2 of Clifford 2 of E. And with this connection, we can define the covariant derivative. So covariant derivative of for example, of a section of E. See, if X is a section of M times E, then covariant derivative of X is just equal to the dx plus omega x minus 1 to the power degree of x. Yes. Well, degree of x equals 1, so this is a just minus x omega. Is this I write in Clifford product? Of course, I can if I forget the just Clifford structure and remember only external structure, this will be the x plus omega. No, perhaps not. Sorry, that's just a formula which allows to write covariant derivative just in terms of Clifford product without indices, without matrices. So this is what is well, very easy computation shows that actually this quantity is exactly the product omega times x is not homogeneous, x omega also, but the difference is homogeneous and of degree 0 with respect to Clifford algebra, and so this expression is quite well defined. And therefore, well, you can also extend this to forms and also compute the curvature of the metric. So this is so therefore we have in our well, main objects in our general relativity will be, well, in our geometry will be the Hilbert, which defines the metric, and the omega, the form omega which is defined the connection. So this is omega, and omega theta is an omega defined connection, define a metric, and connection.
But this is a local picture, obviously.
It's a local picture, but since I can, well, I'll say a little bit. One can glue local picture using this transformation.
Yes, sure.
Glue together. This is just a defined metric and connection on manifold and connection on cotangent bundle to M. Now, having a connection and a metric, you can compute main ingredients, namely, well, the proposition that if you fix a connection and the metric, then you can compute the torsion. So that perhaps I do the following. So recall that the torsion of a metric is well, unfortunately, well, maybe T, I will do boldface T because not to mix with cotangent space. So torsion is by definition, it's something which maps the cotangent bundle lambda 2 of cotangent bundle of tangent bundle to tangent bundle. And
So
of course,
your connection is not, sorry, your connection is not Levi-Civita here. So you consider
so
here-
far not. So far not. But it will be Levi-Civita in a second.
Okay.
Levi-Civita should have zero torsion.
Yeah, that's what I'm asking. Yes.
Here I just take any connection. So omega theta is just any metric and any connection, preserving metric. Now I want to impose the Levi-Civita condition, saying that requiring that the torsion is zero. But for that I need to write torsion, formula for torsion. And the formula for torsion is quite simple. So let's define the using theta. We can send it to E, and this map I would denote by little t. So this is the same thing as big T. Well, t. I recall that t of xy is just covariant derivative of x with respect to y, other way around, yx minus covariant derivative xy minus commutator of xy, and this is a linear map of lambda 2 to tangent bundle, and that's just well, now it's mapped from 1 by 2, so t belongs to omega to 1, 1, 2, 1, 2. It's two form, but with value in my Euclidean space. And there is a formula which is very easy to prove. It's just 5 minutes to prove, but I admit that t is given by just covariant derivative of theta, actually. So covariant derivative of theta, which is equal to d theta plus omega theta minus theta plus theta omega. So this is a formula. You see that with Clifford product, you can write it without any indices, just a very simple expression. And so therefore the theta omega is Levi-Civita.
Sorry, Volodya, really plus theta omega or minus?
Yeah, plus, because here is minus because x is zero form. So actually, number of, if you consider x to be a form.
Okay.
So you have an extra sign which comes from the degree of the form. And actually, this is plus. Yeah. That's really very important that this is plus. I'll explain why. It's, so Levi-Civita if t is equal to 0. And there is an absolutely classical theorem by Levi-Civita that such theorem that for given theta there exists a unique omega such that omega theta. So the metric defines the connection. Omega is Levi-Civita. And I want to actually, nevertheless, lack of time to prove this formula. And for that, I need to do the following observation. So observation, define. It's a kind of crucial point in the rest. So this is let's define some operators acting on. So we can, let star 1 be a Hodge star acting on forms. Star 2 be a Hodge star acting on lambda of my external power of epsilon, which is the same thing as a Clifford of E. So there are in a sense, in this story, there are two Hodge stars. One goes to the base and one goes to the fiber. And let be E the operator, which just takes omega PQ to omega P plus 1, Q plus 1, which is given by E of x equals to x theta x minus 1 to the degree of x plus, this P plus Q x theta. So, and actually the same thing as just you wedge product theta with x. So x, if you consider x as a form with values in external algebra, you just take your field by and you multiply externally by x. So it raises the power with respect to, since this is 1, 1, so it raises the power, the degree in every degree by 1. So this is some operator. And let's define the following operator. This is a F will be just you conjugate E by theta 1, theta 2. Well, right. It's, well, inverse star Hodge squared is minus 1 to something. So in order to get rid of the signs, I just write in this way. So I conjugate theta 2, and well, and this is F maps omega PQ to omega P minus 1 Q minus 1, and I'll define E prime, which will be the same thing, but only with respect to E1. Inverse. And it will be something which P minus 1, Q plus 1. Yes. Sorry. Omega PQ. Omega P minus 1. Q plus 1. And operator F prime, which is the same thing with 2. Minus 1 F star 2. It's F maps to omega PQ to omega P plus 1 Q minus 1. So these operators are essentially, well, also I can define the operator H, which will be N minus P minus Q. Well, it's just takes, it's a diagonal, every form is multiplied by its degree. And H prime, which is P minus Q. In the claim that EF, so, well, once again, what is this this F, for example? F takes, this is a wedge product with this field by. And F is just the internal product of this field by. So internal product of a form, well, vector to form to one form to n form, just substitution of the dual vector. So this is essentially you use the external product. And this one is just external product with one argument and internal product with respect to another. So this is some kind of very easy statement. But the claim is the following, that E1 F1, EF H, and E prime F prime H prime generate the action of SO2 cross SO2. So the computational relation between them is just like SO2. So this is relative of the action of SO2 on homology of Kähler varieties. And actually, well, if time permits, I'll explain that it's actually Kähler Lefschetz SO2 is just kind of particular case of this story that you introduce complex structure in all the business. But so this is a very easy observation. Everything is just linear algebra. Everything happens in one point, so there is no differentials here. So there are some action of this group on the space of these PQ forms. And now I want to prove the theorem. So I want to say that.
Can I ask one quick question?
Yeah.
The Hodge star 1, does it depend on the metric?
Hodge star 1 does depend on the metric, of course.
So it depends on the theta, basically.
It depends on theta, yeah.
Okay,
of course.
thanks.
Of course. Yeah. Hodge star 2 doesn't depend on theta, but Hodge star 1 does. But once again, to verify, for example, the relation, it doesn't matter because we can just take theta. Well, theta up to codant change is always standard, so you can take standard theta and verify. Well, proof of this theorem is really elementary, so it's nothing special. Now, what I want to say, well, this is my favorite picture. So this you can draw coordinates. So this is P, well, or Q, perhaps Q. This is P, and you have the action of the E and F act, well, E prime, F prime acts in this direction, and this is E, this is F, E prime, this is F prime, this is E, this is F, and so you can just and this X is H prime. So H prime is 0 here, here, and here, etc. This is H prime is 1. This is -1. And this X is the X H. And so for example, this is Q equals 2 and P equals 1. And this is the curvature, the torsion, sorry. So torsion stands here. And the theta stands here, of course. And omega stands here. Omega is one form with value in lambda 2, and this is two forms with value lambda 1. And there, so I want to solve the equation d theta plus omega theta plus theta omega equals 0. So I want, for given theta, I want to find omega. But this equation can be equivalent to the statement that d theta equal plus e theta. Well, there is a 2 somewhere which I forgot, but well, it's so far the normalization correct. It's 1st of April. I can, all the 2s are. Maybe I should write 1/2 here. Sorry. Well, perhaps what I wrote so far is correct. This may be later. So it's e prime theta, e prime omega, sorry, equals 0. But the h prime of omega is equal to -1 omega. So the eigenvalue of h prime applied to omega is -1. So the weight of omega is -1. And if you take e prime, E prime, which maps the vector space, the omega to 1 to omega 1, 2, is an isomorphism. Just because of representation theory of SL2. If you have a map E from the weight -1 to weight 1, it's always an isomorphism. And so therefore, you can inverse that. So therefore, omega is given by E1 E prime inverse. It's inversible d theta, and so it's unique. So this is a very easy formula to verify that really the solution exists. And so the fact that there's an action of SL2 allows you to prove something. And I want to, I don't want to repeat other proofs of this type, but there are plenty of such things. So, for example, yes, maybe I'll. Well, this is the torsion. Now I forgot also to mention that the curvature. So the curvature is also some easy expression. So R is equal. Well, you can guess the formula. You can also write down without any independent of its relativity or not. Curvature is d omega plus omega for wedge omega. And also the fact that it's relativity, however, t equals 0 implies that that ER equals 0 because, well, also it's very easy computation because t is equal to d theta plus omega theta plus theta omega. And dt is, well, if you compute this, well, dt is equal to ER. So therefore, the fact that curvature is 0, the torsion is 0 implies that R is actually isomorphic. R is invariant under this operator E. Well, and also maybe another consequence that well, yeah, and R. Sorry, I maybe yes, H of R equals to 2 minus 2 times R because H prime sorry, in dimension 4 E R equals 0. Maybe I wrote wrong thing. Sorry. Yes, no, it's okay. ER. Well, this is no, sorry. This is some details. Well, there are plenty of other things which you can do with that. Maybe I shouldn't speak about that. For example, there is a Bianchi. Well, actually, this is a consequence of that is a Bianchi identity. Well, now I'll speak a little bit about general relativity. So far, it's just Riemann geometry, pure simple. And now the Hilbert action, so S Hilbert, is well, can be written in the following way. So this is the integral over you take just the integral of the curvature. So you take curvature, but curvature is 2 to form. So in order to make it something which can integrate over M, you apply e to the power n minus 2, and you take the supertrace, which is equal to, of course, the supertrace of integral of e to the n minus 2 of r d omega plus omega squared. Once again, this is 2 to form. Then you apply e to the n minus 2, you get n form. So you can integrate it. But the result of the integration will be an n form, n element of lambda to the Clifford to the n. And then you take supertrace and get a number. And actually, this is equal to, you can write down that this is equal to the supertrace of the integral of just theta to the power n minus 2 times d omega plus omega squared. Now you can compute that well, in this way, it's very easy to derive Einstein equations because variation with respect to omega and theta. So this, well, omega is expression quadratic in omega, and also well, polynomial in theta, contrary to ordinary Einstein action, which is a rational function of derivative of metric, and it's very complicated. Here it's very simple as an integral. So delta s delta omega actually is equal to e to the power, well, it's also can be written in terms of, well, I do not make any remarks, that is e to n minus 3 applied to d theta plus omega theta plus theta omega times a constant, which is n times n minus 1 times minus 1 to the n, but it doesn't matter, something here. So this this equation, if it's equal to 0, then it means that this thing is equal to 0. And once again, if you compute weights, then e to the n minus 3 in this, for this particular weight is an isomorphism. So therefore,
Can I ask a question? Sorry.
Yes, yes, of course.
So so what are the variables? So are theta and omega independent, or
Yeah, theta and omega are completely independent. Yeah, yeah,
okay,
exactly.
then it's Palatini. So
This is Palatini, of course. This is just Palatini. This is just Palatini.
So I thought you just defined theta in terms of sorry, yeah, I thought you defined omega in terms of theta. But
No, but I define. I just it gives the equation of motion. Just I'm explaining now that the fact that theta and omega are connected is just the consequence of the fact that the variation derivative with respect to omega is 0, because the duration with respect to omega gives you the condition that the torsion is 0.
Okay, thank you.
What is somehow what was surprising for me then I computed all that if you introduce fermions in this picture, which I don't want to do in details, but if you introduce fermions, and fermions are introduced by adding to the action some term with omega times something, so you have the this equation torsion zeros, well, deformed.
Fermions will give you non-zero torsion, right?
Fermions give you non-zero torsion. Yeah. Well, of course, this was known, but the fact that Einstein equations, strictly speaking, are not valid for fermions, for me, it was in the standard form. For me, it was kind of surprising thing. But yes, exactly. Well, there is also a story how to introduce supersymmetry, though this business, but well, definitely I have no time to explain that. And moreover, it will be too much Poisson derivative. Well, and well, the fact that the second derivative with respect to Hilbert gives you actually the, strictly speaking, the Einstein equation, which is in this form. It looks like the e to the times n minus 2 of the d omega plus omega squared is equal to 0. Well, sorry.
Oh.
Times also some constant. So the fact that this is equal to 0 doesn't imply that this equation equal to 0, because e minus 2 is not an isomorphism. But however, this fact that this is equal to 0 is equivalent to the fact that f applied to d omega plus omega squared is equal to 0. And this is just, if you compute it, you can verify that this coincides with the g equals to 0, where g is the Einstein tensor. So this is a standard Einstein equation for the empty space. So you see that, well, I just gave some examples. You can compute plenty of other things. You can compute, for example, Weil tensor in this terms, and verify really Weil tensor is conformally invariant. That Weil tensor will be just e times the curvature. So this is a plenty of other objects you should compute. You can prove it's well, all the computations are really very simple.
I have a quick question.
Yeah.
Back a couple of lines where you define S.
Right.
Are you assuming M to be compact or the metric asymptotically flat or something like that?
No. Of course, it's just local consideration. It's just everything is absolutely local. So topology of M doesn't play any role. So you can take any manifold.
But the integral of S, the integral defining S.
Yeah. It's just, well, it's variation of problem. So I solve the corresponding differential equations.
Okay.
I write the differential equation. I do not ask myself the question of existence, etc. So of course, the existence of global solutions of that. This is a well, it's a question, but variational problem can be formulated on any manifold.
Mhm.
And the differential equation can be written also on any manifold. Well, maybe I didn't understand the question. So far, it's really local. As well as usual, derivation of Einstein equation doesn't take into account the topology of the manifold.
I guess
Well,
the question is, since you're integrating over M, is the manifold compact, or is the integral somehow some? Are you integrating over some patch where it's trivial? Or?
Well, this is somehow the yes. Well, you may imagine that you integrate over maybe manifold you may allow even be non-compact, or well, manifold with both, perhaps compact with boundary. That's the simplest possible way. Or you take well, you want this integral to be converted. But the standard argument in variational thing, you write an integral. You suppose, and you want this integral to be locally minimal. So if you deform your function by a small amount, then this integral should change by a small amount, will increase. If you deform your theta compactly, what is important that these variations be compact with compact support, and the integral can be on infinite manifold. Well, you may consider just cut your manifold into pieces of compact pieces, and then each require that this equation should be satisfied on every compact piece, and then the solutions glue together. Well, it has to do something with, well, the last 5 minutes, which I want to well, it's a little bit remarkable, which I nevertheless want to speak about. That well, 1 minute. That if E is complex, E is Hermitian. Then in this case, you have an operator which have theta and theta bar, because you have two complex, well, you can decompose your real theta into sum of something of type 2,0 and 0,2. And therefore you have, instead of, you have E and F, you have if, well, if prime F prime, you have an algebra, Lie algebra of rank 2, instead of Lie algebra, of arc 4, sorry, algebra of rank 4. Because you have 4 pairs of E and F. Everything is doubled. You have a theta bar involved. And they generate SL, the algebra, which is not SL2 cross SL2, but larger algebra, which is SL4 hat, which is an affine SL4. And this is really what's surprising for me, that Kähler geometry, it actually, all that describes complex geometry, Kähler geometry, and this is this SL4 hat. And the Lefschetz group is just actually some SL2 subgroup of this SL4 hat.
You want to get the Lie superalgebra somehow here?
I think I will if I, well, it was some project with Verserganova to get it, if you consider fermions, but so far there are no fermions. If you consider fermions, get
I thought there was some mention of Lie superalgebra in this case in the literature, but I cannot, I have very vague recollection. So it may be described somewhere.
I hope that, of course, supersymmetry, definitely want to describe supergravity in these terms, and then I expect some superalgebra. But you know, this group is kind of coming from some site which is not really the symmetry of your system. This is the symmetry of the space of your fields, which we consider. So this is a kind of orthogonal. This is 4. This 4, for example, has nothing to do with the dimension of the space. It's true for any dimension. Like SO2, F2, SO2 says, it's also something which is not. Well, this is really, I have no time, but I'll say really a little bit about the segment. So the phase space of our space, phase space of our theory. Well, you can look at this section, this action, what you write here, and this space is can be interpreted as a pairs of theta and omega, with and the symplectic form, which is W, which is not well, not to be confused with omega. It's integral of super trace of very simple. This is d theta e to the n minus 2 delta omega, and you can very easily verify that really this makes sense. So the degrees are such that you can integrate and get something on 0. So this is in a sense, this quantity, this is a symplectic form. E depends on theta, of course. So this is nonlinear symplectic form on the space, but can be written this way. And now the groups, the symmetry groups. First of all, this action has two symmetry. Well, gauge theory symmetry. And this gauge symmetry is very simple. So it's theta omega goes to g minus 1 theta g and g minus 1 omega g plus g minus 1 dg. So this is can be written in the standard terms. Just you can verify that if this well, for example, it preserves the action. And this gauge symmetry has a very natural generators. So generators, which is it's J, which is equal to e to the power n minus 3. The covariant, well, the covariant derivative of this is a covariant derivative. So this covariant derivative of theta to the n minus 1. So it's t to the power n minus 2, theta n minus 2 plus theta n minus 2. So this is a generator of the so the Hamiltonian, which corresponds to the gauge transformation, is given by integral of supertrace of epsilon times j, where epsilon is the generator, infinitesimal generator of the h epsilon is equal to that, and you can verify that the Poisson bracket of h epsilon prime is equal to h of commutator of epsilon prime. This is no problem with that. But the problem is the following: another thing is diffeomorphism symmetry. And the diffeomorphism symmetry, once again, what is the diffeomorphism symmetry? I have what is a phase space? The phase space, by definition, is the phase space. That's the space of solutions in the vicinity of the border of the equation of motion. So this of delta S equals 0, our Einstein equation in the vicinity of the border. And the diffeomorphism moves the border. So what is the answer? How incorporate the diffeomorphism symmetry into Hamiltonian point of view? And the main idea that there is a groupoid behind, and actually the diffeomorphism symmetry becomes a groupoid. So we have a GR groupoid. By definition, is the following object. So this is a solution, a pair, a solution of delta S equals 0 on some manifold. I'll do the following: n manifold, and dimension of n is equal to -1. On n times the interval 0 epsilon, comma, a map isomorphism phi, which goes to n times 0 to n times epsilon. So you have two components of borders. You have a solution which is defined between them, and you have a map between these two. This is clear that if you have, and so therefore, of course, you have a map from this space, from the group point, to the space of solutions. Two maps to the space of solutions in the vicinity of n times 0 and n times, well, maybe it's better to call 1. Yeah. N times 1. So you can, and this is just the the groupoid, this space, and there are two maps, target and source target maps, are just the maps from this side and from this side. And this is, you can glue such things together, provided the source of one is equal to the target of another. So you have a solution on one cylinder, which coincides with the solution of another cylinder. Of course, you can glue these two cylinders. And if you have an isomorphism between the sides, then they compose them and get isomorphism with the external sides. So this is something which you can glue together. If the size of this cylinder is 0, this corresponds to just the ordinary formulation group. So, well, if you consider the solutions which are essentially constant with respect to these coordinates, doesn't depend on these coordinates, and you get the subgroup, which is the diffeomorphism group of these three manifolds, which is a subgroup of this groupoid, the group of automorphism of each object. And so this, and well, what quite obvious that if you have a vector field which is not necessarily tangent to the border, then you can move your boundary a little bit along this vector field and obtain a cylinder and the identification with the this side of the cylinder with this side of the cylinder along the vector.
Okay. I'm not sure. Phi is a diffeomorphism of what?
Diffeomorphism of three-dimensional manifolds in R.
Okay.
Of finite dimensional manifolds. So assume you have a vector field, which is, this everything dimension is real world, is a dimension 4, and this is dimension 3, and then you have a diffeomorphism of the boundary. Well, I draw it's compact, but it's not necessary.
But maybe I'm naive, but if you say it's a map from n times 0 to n times epsilon, this amounts to the fact that this is a map from n to n.
You have no identification between the two, canonical identification.
Okay, fine, but still.
So you fix this canonical identification. So fix it, say it's canonical. So you need to fix the identification. Otherwise, you cannot, for example, speak about Hamiltonians because you have a map from one manifold to another manifold.
Sure. So basically, you're just saying it's a torsion instead of saying it's a group, but it's still isomorphic to diffeomorphisms of n-1 dimensional gadget.
It's still isomorphic, but this part, because the most important part is just the solution, which I fix.
Okay.
And this is kind of small part of the data. And the big part is the space of solutions, which I fix from on both sides.
But do you assume that topologically your 4 manifold is a direct product of some fixed m to the timeline, by the timeline?
In order to define the groupoid, yes. But in principle, I am speaking about m, any m. And as always, so this phase space, you have m, you have some manifold m, and you have boundary of this manifold. And on every boundary component, which is one dimension less, you associate a phase space.
You have kind of some kind of cobordism category, actually. So,
something
to
like
solutions
that,
of Einstein equations.
Yeah. You have a cobordism category, so you have a solution of something which, you can restrict. You have for every component of the boundary, you have some symplectic manifold S, and you have the product of symplectic manifolds with boundary components, which can be, this shouldn't be a direct product. I do not use anything about the time. But of course, in the vicinity of every boundary component, you have, you can, the vicinity of boundary component is of course a direct product. Non-canonically, but it's a direct product.
You are assuming that the boundary components are space-like, is that right?
Yeah. If you have if you're speaking about real gravity signature 3+1, you want boundary to be space-wide, of course.
And also you need some conditions. So because you have just Cauchy surfaces basically, and so you need some well, standard conditions satisfied by the geometry of this Cauchy surface, perhaps.
Well, the conditions. Well, there is a. So what I said is correct. So that well, these two maps are not onto. And what you're speaking about. So these maps are not onto. Well, maybe I should say the following thing: that here there is a Lagrangian submanifold L, and this Lagrangian submanifold is actually if you restrict the solution to the boundary, then you get a submanifold as the product of symplectic manifolds. And this submanifold is not any Lagrangian; it's half-dimensional. Well, everything is infinite-dimensional, of course, but it's half-dimensional. It's Lagrangian. And in this case, well, you have these conditions. If you wish, this Lagrangian manifold has a certain conditions, and of course, it's Cauchy surface, which. But this is just the fact that these conditions amounts to the condition that this manifold is Lagrangian. But if you have a cylinder, so you consider the solutions here, and you have solutions here. If you consider all solutions on this boundary, on this cylinder, and you restrict it to one boundary only, and forget about the behavior of the another one, then you have a map onto. And this is your phase space by definition. Because you have just solutions which in the vicinity of this boundary. It's kind of unlimited, unrestricted. You don't care what happens on the other far away from this point, in particular on the second boundary. Well, I cheated a little bit here, honestly. You need to require, well, for gravity, there is something you need to impose additionally. But if you have, I don't know, Young-Mills, you have no restriction here. Well, what I was trying to do the last few days in order to prepare that, but really write down explicitly the commutator between the Hamiltonians corresponding to the groupoid, and well, hopefully I will finish the computation soon, but I didn't finish them. And well, the answer is that the HV1 and HV2, the Poisson bracket between the two are not, of course, the commutator of V1, V2, because V1 and V2 do not exist. V1 and V2 are vector fields which are defined only on the submanifold of codimension 1. So, and they are not tangent to the submanifold. So this is cannot be true. So this is, well, something which there is some expression which depends actually on the point where not only vector fields, but also depends on the theta norm explicitly, not only on the commutator. And this is just was. Well, I tried to ask myself the answer. What is the moment map in terms of groupoid action? Because here we have definitely groupoid action, which is symplectic and everything is fine. But sorry for terrible overtime.
Well, thanks very much for your nice talk. So let's thank the speaker first of all. And yeah, do we have any more questions?
Yeah, I have a question. So do you have any idea what the momentum map is?
Well, I wrote here the momentum map. Yes, I even have some conjectural formula, which the simplest one is that HV is, well, which is, well, perhaps it's correct, but HV is the integral of V over I V theta times just the Einstein tensor, which is equal to integral of IV. Maybe not Einstein literally, but it's e to the n minus ev theta times e to the n minus integral over the boundary of m e to the n minus 2 of the curvature. So you take curvature, you take the form which is n minus 3. Sorry. So this is e to the n minus 3 of curvature. This is a form of type n minus 1 comma n minus 1. Then you multiply by something which is, this is 1 0, and you get something n comma n minus 1, and this is a Hilbert trace. So it's n minus 1 form, which can integrate over that. And this is this is expression which just gives well, this is more or less. There is some other term which I cannot manage to cancel, which is more complicated, but this is, it's more or less the same. But what I want to say that everything is theoretically easy to compute. It just one needs to sit and compute and find all the signs, put all the signs together. But this is HV is just a Hamiltonian, which well, you have for example, for this groupoid, you have two maps between symplectic manifolds. One you have symplectic manifold related to this boundary, one symplectic map belongs to this boundary. So one map is given by the solutions of the equation, Einstein equation between the two, and the other one is given by the map between the boundaries. You have two maps, so you can take a ratio of the two. You get a map from the symplectic manifold to itself, and if you tend to identity, then you get a vector field, and you can compute Hamiltonian vector field. So, everything is well defined.
So you doing some computation for the Lie algebroid of the groupoid rather than the groupoid itself?
Right. I do computation. Just I know the vector fields for which you compute the Hamiltonians, and then I need just to compute the Poisson brackets between them in order to verify what relation they satisfy. Because they cannot satisfy the relation.
Right?
It's a Lie algebroid, yeah. Over the space, the phase space. So you have the phase space and you have vector fields. Yeah.
So in the work that I've been trying to do with Christian Bloman and Michele Scavina, we have tried to express the constraints as a momentum map. This seems to be different because you're already assuming that you're with solutions of the Einstein equations, so the constraints are everywhere zero. Is that right?
Yeah, right. You are using which formalism also, because a little bit, well, the constraints are really very different in if you consider metric, for example, metric first and second quadratic form, which is Gauss-Kadatse equations, which are constraints.
Yeah, we're looking at that formulation.
Form, yeah. And this is, well, there is this theta omega form, which constraints are, well, it's also the constraints is actually the fact that the gauge Hamiltonian, all gauge currents should be zero. So it's written that this is zero, and this is the constraints which are equivalent to Gauss-Kadatse. So you somehow these constraints are satisfied. You need to impose them, and then the other on the space of solution of this constraint, you can resolve that constraints. But once again, it's a little bit 1st of April fruitful joke. So this is, I am not 100% sure the computation especially turns out to be more complicated than I expected.
There's a question from Dima also.
Thanks.
Yes. Hi, Volodya.
Hi.
Yeah, I was just, I wanted to ask what the target space of your momentum map is. I think this kind of like already emerged from the preceding discussion. It should be
Right. Well, this is well, the target. Well, I cannot say very well, but this is something which is you have the dual space to the vector fields. So this is your phase space. So this is the space of all pairs theta omega, and the dual space to vector fields. So this is a dual space to vectors. So these are just omega 1 sections of something f.
Cotangent density, covector density.
Cotangent density. So
covector densities.
Yeah. So this omega, this omega 1 tensor omega n minus
1. Thank you.
But this is really they depend also of theta or no. So this is not just vector fields, but.
Yeah, and Ezra has raised his hand also.
Yeah, hi, really stimulating. So I'm just curious, you suddenly introduced a rank for Lie algebra, SL4 hat. So I was curious what the Cartan subalgebra was.
The Cartan subalgebra is just, well, as before, Cartan subalgebra is something which is constant on every homogeneous component. So here, for example, what is Cartan subalgebra? What was Cartan subalgebra for SL2 cross SL2? They were H was n minus p minus q, and H prime is p minus q. And here is something like it's one generator will which H0 will something like p plus n minus p. I don't remember by heart. So it's p plus q minus n. Another H2 equals H1 is equal to p minus q bar. H3 equals.
Right, I see.
Equals something like p bar minus q, and H4 is n minus p bar minus q bar. Something. Yeah,
I see. Yes, of course. I got a little bit confused because you're writing p comma q, and I keep forgetting that that's got nothing to do with the Kähler. So once you've got the Kähler,
it's nothing to do with Kähler.
You have four indices, right?
Right.
Okay.
Right. You have four indices, and PP bar are usual Kähler, QQ bar are usual Kähler indices, and PP bar are just these indices.
Okay. Thanks.
Yes.
Yeah, and then there's another question from Ted Voronov.
Yeah, hello. Sorry for asking too many questions, perhaps.
No, that's very nice.
Yes, yes, I have two questions. So in the beginning, you said just a remark. In the beginning, you said that you don't like calculation of indices. And basically, my question is, so your formalism, all these operations, EHF is efficient, supposed to work as a replacement of calculation of indices, right? Right. Of course, I verified everything with indices. So this is not. Yeah. So there's a bit of cheating. So because when you cannot just avoid writing things on indices.
Well, I wanted to be sure that what I do is correct. So I use some formalism, but essentially, in order to make the computation, you don't.
Yeah, but very nice formalism indeed. So I like indices, but the formalism is very nice.
Really.
So. Right, and another question is a rather stupid question. So your Hilbert is described as a form of degree 1-1. So the second one refers to Clifford algebra, the grade in the Clifford algebra that you introduced.
Right.
Does it make sense to consider just something of one star, so to say. So just replace by some arbitrary odd element of a Clifford algebra, or perhaps even just consider odd with respect to total grading. To get like super connection.
Yeah, I understand your question. Yeah, well, I actually didn't think about that. I was what I did think that you can consider also, instead of well, theta, you can consider, well, you have theta omega, and you can put something in between, which is, well, can call psi, which is omega 1 with values in actually the representation space of the Clifford algebra. The representation space of Clifford algebra is a half of a spinor, a half of a Clifford algebra. So it's tensor square root of Clifford algebra.
You can try to realize Clifford algebra as an algebra of differential operators on some odd space.
Odd space, exactly. Yeah. So this is well, this will be well, if you pronounce beautiful words, it's a Rarita-Schwinger term, which is one form with values and spinors. So this is a and
Rarita-Schwinger field, yes.
Field, yeah, and this will be
vector spinor.
Yeah, and with well, go not up in dimension, but kind of down in dimension, not 1 but 1/2. So omega 1, in a sense, it's omega 1/2 1. And this I did, but with going higher in, well, maybe not, but also for me, I try to keep this symmetry between P and Q, which, well, I like very much.
All right.
Yeah,
yes,
so maybe for that reason I did, but well, it's a good idea. I'll try to think about it.
Yeah, you can start from just an arbitrary form with values in Clifford algebra, and then say require that, well, impose some initial conditions, so to say.
Let's see.
Okay.
Yeah, well.
Basically, the form that you consider plus some tail.
Yeah. So you can take just odd form, not necessarily degree 1, but odd form of any degree.
Yeah, but you still need some kind of non-degeneracy to be able to
use in this first term. Yeah. Good idea. Well, honestly, I didn't try this. I should, but I should.
Okay, thank you.
Yeah. Maybe I have myself a little question, probably a stupid question, but when you got rid of the coordinates, but you're still working with a local frame, I would imagine probably you can make it even frame free by just directly working on the frame bundle. And so it's, so to speak, some SL2 times SL2 symmetry naturally living on the author.
Well, good question. Well, it's a kind of, let's same thing. If you have a gauge field, for example, if you have a connection, you write this D plus A. So where A is a one form value in endomorphism, but for that you need really to trivialize your connection. So in order to really have a, well, if you have non-trivial connection, then this not, well, you have on every patch you have your A, but different A's are connected by gauge transformation on different patches. So this is the same problem somehow. So if I want really to be one form with values in an algebra, then I need to trivialize my or just consider it locally and then.
I'm just suggesting directly working on the principal bundle, and then you have a connection form on the principal bundle.
Form in the, well, yeah, maybe you should you should think of that as form in the. Maybe one can do something. Yeah, certainly. I agree that. Well, so far I was thinking mainly locally, but could be done globally as well. Yeah.
Just these local forms assemble in a single form on the frame bundle.
Yeah, and maybe in my context also it could be done in some universal way. So single form in some bundle, but which Clifford, but they are kind of collected. Yeah, good question. What is the principal bundle in this context? Very good question. I just didn't think about that at all. But
Okay, any other questions? Good or otherwise? No, if it's not the case, then yeah, let's thank Vladimir again.
yes, thank you.
A lot.
And possibly see you next week. I believe next week is Asia-friendly schedule. I don't even know who the speaker is. Nikita, do you know?
Yes. The speaker is Yoon-Hee Sheng from Jilin University. The title is Deformations, Cohomology and Homotopy of Relative Rota-Baxter Lie Algebras.
Okay. Thank you. Bye-bye.
Okay, bye everyone. Thank you very much.
Thank you.
Bye.